Okay, today I will start talking about so-called pair production. So before pair production, let's consider something even simpler. Can a single electron absorb photon, right? And we can do the picture of this. So there is like a stationary electron. So this is E, and photon comes in. This is photon. So this one is before the collision. So this is before. Hopefully you figured that by now photon is kind of like a particle in this kind of experiment. It can collide with particles like billiard balls. And after the collision, so this is after, so this is electron going with some momentum p and no photon. So this question, is this even possible? Any suggestions? How can we check something like this? What are we supposed to do to determine if this is allowed or not? What is the principle? Exactly. We need to write momentum and energy conservations. So momentum, before I have photon momentum, h nu, and if I divide by c, this is the momentum. And after, there's only electron momentum, which is p. And we need to write conservation for energy. Before I have h nu. Anything else? Yes, good. That's the one I always forget, so that's why I ask. So this is mc squared. And afterwards, the energy is only the relativistic energy of the electron. This is p squared c squared plus m squared c fourth. So let's work this out. Maybe I can take the square of this. H nu squared plus m squared c to the fourth is equal to p squared c squared plus, okay, there's also a cross term that I need to write, plus 2h nu. Let me push this to the left. So the cross term is 2h nu c squared. Okay, and there's nothing else. And on the right hand side, I have square of square root, which is p square mc square, p square c square plus m square c to the fourth, and cancel this with this. And for p, I'm going to use this. So this is going to give me p square c square is going to be equal to h square nu square. Then this is h nu square. Then this h nu square is going to cancel this one. And this is going to give us 2 mc squared h nu. Anything else is equal to 0. So m is electron mass, which is a fundamental constant, so that's non-zero. C is speed of light, which is a fundamental constant, non-zero. H is also. Then this tells me nu is equal to 0, right? But if nu is equal to 0, photon momentum is 0, basically there is no such photon. So that means nu is equal to 0 means there is no photon, no such photon. Then this process is not possible in nature. Any questions or comments? But then if this is not allowed, we have to ask the question, how is the photoelectric effect even possible? So we are saying now an electron cannot absorb photon, then why have we been talking about photoelectric effect in the last few lectures? Any suggestions? Should I pick somebody and ask? Anybody? So is photoelectric effect possible? Yes. But we just showed a photon cannot be absorbed by an electron. What is missing? Yes?
It's not have a mass.
Uh-huh.
Is that a particle?
Electron does not have a mass,
Yes.
but electron has a mass, right? We know that. Yes?
Is emitted by electron after?
But in the photoelectric effect, light comes in, right? Or like the reverse, right? Light comes in, an electron comes out. At the end, light is completely absorbed. And the
Because there the potential energy from
uh-huh,
it works against the potential energy of
uh-huh.
proton, so
Potential energy of proton
yes.
nucleus. Yeah, very close. There is like yes.
Is it because it's not on the atom itself? I mean, if it says nucleus, it will be increased in the...
Yeah. Yeah, basically, yeah. I think these two answers are, I think, good enough for my taste. Yes, go ahead.
It is not possible free electron.
Yes, that's also exactly the case. This entire thing takes place in a solid, right? And solid has like so many other things around, like the nucleus, or there could be other like things that can absorb momentum, or vice versa. They can like satisfy the conservation laws, and the process we are interested can still take place. So the answer is PE, photoelectric effect, takes place in materials. It's not free electron. So this was the preliminary calculation. So now let's do pair production. Pair production. And in the case of pair production, what happens is, okay. So what happens is like photon comes in, photon, and there's nothing, but suddenly an electron and a positron emerges. So this is, let's say, this is electron. This is, okay, this is minus E charge is electron, plus E charge is positron. They emerge, and they emerge in a symmetrical way to provide the conservation laws. So you can see total charge is equal to minus E plus E is equal to 0, both before and after the collision. But that's not enough. We also need to write energy and momentum conservations. Here I have, maybe I write with energy is equal to h nu, and momentum is equal to h nu over c as before. Yes?
Before the collision, there's only an electron and photon, right?
There, before the collision, there's only photon. Photon comes in, suddenly in the empty space, an electron and a positron just emerges from nowhere, but photon disappears. That's the pair production. That's what we are trying to decide, if this is even possible. And after the collision, so energy is, because these are like particles with mass, we need to have p squared c squared plus m squared c to the fourth. Basically, electron mass and positron mass are the same, and this is square. So, like, because there are two of them for electron and positron, I have to multiply this with 2. And also for the momentum conservation along the x direction, I need to have, let me just write the momentum because there are so many p's. Momentum is equal to p cosine theta times 2. There are two of these. And because, okay, you could choose these angles differently, but you would come up with the angles to be the same because of the conservation along the y direction. Okay, so basically we are going to use these equations, and we are going to, okay, the first one is h nu should be equal to 2 times, okay, let me write it as I wrote above. So this is p squared c squared plus m squared c to the fourth. So this is the energy conservation. And the second one is h nu over c. H nu over c is equal to 2p cosine theta. Or from here, p is equal to h nu divided by 2c cosine theta. Good. So I'll take the square of the first one. H nu squared is equal to, maybe h nu squared over 4 is equal to p squared c squared plus m squared c to the fourth. But I have p here, so I'm going to substitute that. So this p is going to come in to here. So this is h nu squared over 4 c squared cosine squared theta. Did I miss anything? Times c squared. This c squared plus m squared c to the 4. So cancel that with that. And I'm going to take this thing to the left hand side and take the inside the parenthesis of h nu squared over 4. There is 1 minus, I think h nu squared 4. This is 1 over cosine squared theta is equal to m squared c to the 4.
Sorry, can you go?
Yes.
That h nu over c is equal to 2p cosine theta. Where was it?
So it comes from momentum conservation along x direction, right? I use momentum conservation along y direction to determine this theta, and this theta should be the same. And momentum conservation along x direction is like photon momentum is h nu over c, and electron and positron, they have the same momentum, but I have to project in the x-axis 2p cosine theta, right? P cosine theta times. Yeah, good point. Thank you. Now I look at this equation. So first of all, so this side is a square of a, right, square of a number, so this is positive. So this side is mc squared, which are positive constants, so this is also positive. So this is 1, and I know 1 over cosine squared theta is something bigger than 1, because cosine theta is always something less than 1, right? So this is bigger than or equal to 1, so this whole thing is negative. So I multiply a positive number with a negative number and get a positive number. That's not possible. Is that correct? Then this is also not possible. Not possible. However, we know pair production takes place. But it happens in the presence of like a very heavy nucleus, because it happens in nuclear materials like uranium, which has like a gigantic nucleus. Like let me just represent it like a gigantic nucleus, and in the presence of this nucleus, maybe I can write it here. So photon comes in, exactly like what we wrote above. So this is electron, this is positron, this is electron, and the excess nucleus, because it's like so heavy, it can provide necessary momentum, and its energy does not change at all because its mass is like huge. So pair production happens exactly like photoelectric effect takes place in materials. Pair production happens near nucleus of like heavy atoms. So let's estimate the orders of magnitude for this process. So the order of magnitude, like after the pair production, I need to have at least 2 mc² excess energy, right? Initially there is no mass, there is only a photon, and we said change in energy of the nucleus is negligible. So initially we have only a photon. Afterwards we have like 2 particles with mass, and then this extra energy, which is the minimum requirement, right? To be able to create something like this, you need to be able to create the mass, but the mass comes with energy cost, and this energy cost should be equal to photon energy, which is h nu. So here is a good number to remember. So m is electron mass, c is speed of light. So m electron times c squared. This is like an energy unit, and a very good scale for this is like MeV. So this is going to be 0.51 MeV, mega electron volt. Then we need at least 1.02 mega electron volt energy. So this is the requirement for frequency, and this frequency corresponds to so-called gamma rays. Okay. So now, like if you remember, we started like the electromagnetic spectrum is gigantic. We started with what we know, which was the visible. So visible, and in the visible we had photoelectric effect, and higher in energy we had X-rays, and for the X-rays we had Compton effect, right? Basically an X-ray can scatter off electron, and we can like detect this through the Compton experiment, which we talked last time. And now if you go even higher, you have gamma rays, and this one is pair production and nuclear matter. So that's why you need radioactivity to reach the gamma ray physics. Any questions? Any comments? Yes? Why did we take m? So because like I could basically take them to be different, but like because there is no initial momentum in the like vertical direction, right? I would find the angles to be the same, right? Yeah, I think you can make it into an equation, but you don't need to, right? Yeah. Yes.
What exactly in the nucleus of a uranium atom triggers this effect? Do we know?
What triggers is exactly this, right? Like if you like in physics, everything that's allowed generally happens. What is allowed and what is not allowed is determined by these kinematic equations: conservation of energy, conservation of charge, conservation of momentum. And what determines is exactly what we talked here, right? So energy, momentum, and like charge, they are all good in the presence of the nucleus. Then this process happens. The only requirement is you have to have enough energy, right? Like if you try to do this with visible, it is not going to happen because you need at least 2 mc squared energy, which is 1.202 MeV, right?
What is the role of the uranium atom?
So your uranium atom is like providing, right? Like this calculation showed us if it was like just empty space without any uranium atoms, this is not possible. Kinematically, it is not possible. Energy and momentum conservation, this calculation shows, does not allow a process like this. However, if I have the uranium atom, I can like provide necessary momentum by, right? Maybe this guy is going to recoil in one direction. We don't care, right? That's like at this moment it's a much more complicated calculation, but we don't care because it has like there's like a mountain here, and whether this mountain moves or not is not actually very important. You can completely neglect, and you can just focus on what is here, and what is here is like a pair production. Does that make sense?
Kind of.
So the only requirement is you need to go to gamma rays because you need the order of MeV. As long as you reach that, like you have uranium and you just send the gamma rays, pair production will happen.
So, in the second derivation, what happened to the PC square? So why didn't we use that?
So this derivation,
Yeah, why didn't we use this in the...
no, we used it, right? Like, so this is energy, here is energy. So this one is momentum. And I took the square of this one, and this is h nu square over 4, right? This 4 came here. There's p square, c square, m square, c to the 4th. And I had to eliminate p square here using the second equation.
Yeah, I understood this. But in the gamma ray section, we didn't use this. We only used mc squared. H nu is equal to mc squared in the last part. Can you move?
Oh, this is like an estimate, right? So
Yeah.
I am still estimating exactly the same process, right? So for this process to take place, you see, there is like energy here, and what is like, if you focus on this equation, the first equation, what is the minimum energy you need for this to take place? The minimum is determined by minimum P. I can put P is equal to 0, right? I can create electrons, but they can move infinitesimally slowly, but they still need to mass because in the energy, I need mc squared. And that determines the threshold. And the threshold is gamma rays. Yeah, good point. Thank you. Yes.
1.02 was the threshold for high energy.
Yes.
What is it for intermediate and lower?
So for like intermediate and lower, I'm going to draw like a line in a little bit. It determines what kind of material you are working with. It depends on like which scale you are probing. Maybe I can just mention and you can ask me again if that's the question you are asking. So let's talk about that real quick. So basically we have these 3 processes and they all take place depending on the scale you are working. So let's think about like a probability for a process to happen. So this is probability, and maximum probability is 1, and this is energy in eV, and of course this is photon energy because we are always sending photons. And because it's nicer to draw, let's just start from like a logarithmic scale. This is like 0.01, this is 0.1, this is 1, this is 10, and this is 100. So basically, small EVs like 0.1 to 0.01 to 0.1 are visible, and in that range, maybe I can start with photoelectric effect, right? It just goes like something like that. Right? This is photoelectric effect. And in the intermediate range, maybe I can use blue, you slowly transition from photoelectric effect, and then Compton scattering takes over. And then if you are like keep increasing, it's at some point going to decrease. And maybe in the highest energies, which is 1.02, right? Maybe I can use red. 1.02 and higher, I have gamma rays like this, right? So this is Compton. This is Compton. And this is maybe pair production. So you can see the answer to your question. So this is, for example, I took this data from for carbon. The answer to your question is yes, pair production has a threshold which is 1.02 MeV. But Compton and photoelectric effect, they don't have that threshold, right? They happen in their interval, but they continuously increase and decrease. But if you go to, for example, another material, for example, lead, okay, maybe I can just copy this same figure. So rather than carbon, let's just go to okay, this is lead. Because the nucleus is a little heavier, right? You can provide more, like in the pair production, there's like a carbon is lighter atom, lead is heavier atom. So what is going to happen is like, okay, I have the data here. So this PE goes all the way, maybe something like that. Something like that. Blue. Okay, I think maybe something like that. So the answer to your question is like it depends on the material you are working with, but general picture is like there is some region for photoelectric effect, some region for Compton effect, and some region for pair production.
And here, for example, if the photon energy is around 10, it's a bit vague for me. How can we define like this for Compton? Or
So this order of 10 EV, what is vague? How can we define what?
how can we define it's for like high energies, for gamma rays, or for X-ray?
How can we define? I think like in the spectrum, right, it is not like, oh, 10 EV is gamma rays, right? It is not. It is actually exactly what you said, it's vague. Typically, X-rays start from like order of like, I don't know, like if you look in terms of wavelength, order of angstrom, and it decreases all the way to like, I don't know, 0.1 angstrom, right? It's not like anything below like 0.1 angstrom is not X-ray. We don't say that. Like, and exactly for the gamma rays, right? Anything in terms of wavelength, 0.01 angstrom is gamma rays. We don't say that. You have to keep going a little bit further. And the transition is definitely vague. There's no sharp boundaries. You should think of it as like exactly like colors, right? If you look at the colors from like red, green, blue, it's not like at some point there's like a sharp threshold, red turns green. Like if you just zoom in with your pixels, like it continuously changes. At some point it's vague. Which one is green? Which one is blue? I don't know. It depends on who is looking. So these are just names we call gamma ray, X-ray. Okay. Any questions or comments? So okay, so maybe I can finish. Okay, there's actually 2 more notes, and then maybe we can take a break after that. The first note is inverse of pair production is also possible. Inverse of pair production is, we call it pair annihilation. It's also possible, and the kinematics is like something like that. I don't know, positron comes in, electron comes in, and they annihilate each other, right? Charge conservation is good. There's plus E, minus E, and then there'll be one gamma ray, but one gamma ray is not typically sufficient, so you need two gamma rays. So what we say is like plus E, okay, maybe like a plus E minus E goes to two gamma rays. So this is also possible. And the second note, I want to close with this remark, and then maybe you can continue in the second hour. So a wave which is light behaves like a particle. Then there is like a vagueness in between deciding waves and particles, right? It seems like what we have known to be wave is actually not quite a wave. Can we also reverse this? Like, then, is it even possible? Is it possible for particles, for example, this object with mass, billiard balls or baseballs, like, is it possible for particles to behave like waves? And the answer will be yes, and we are going to call them matter waves. Matter waves. And we are going to consider them in the second hour.